Is everyone in it? Yeah. Okay. Welcome to the last session before lunch. First, a reminder that after Sam's talk, we go for photo op. So follow our staff who's outside. So before lunch. Okay, so we have two speakers. So first speaker is Aishik Ghosh from School of Physics at Georgia Tech. And he's going to talk about before asymptopia, high-dimensional inference in small sample size regimes in particle.
Thank you. And thank you for the invitation. I always really enjoy coming here to CMU. So indeed, I'm going to talk about statistical inference in particle physics. You've heard a few talks about this before. I'd like to start by talking about a moment thousands of years ago when there were a couple of black holes that were encircling one another. And at some point, they got so close, they eventually collapsed into each other. And that violent event created ripples in space-time itself, and that propagated in all directions. It propagated for thousands and thousands of years until 2016 when it reached the Earth. And we were waiting with two LIGO detectors to detect the stretching and bending of space-time. And with that one detection, we were able to claim a discovery of this new concept known as gravitational waves. Particle physics had a similar moment in the 30s when we had one image, and you could look at this trajectory that seems to have been left by some particle, and by just looking at the bending, we could convince ourselves that we must have discovered a new particle called the positron. What's common amongst these two very seemingly different discoveries is that both of them are single event discoveries. One event completely allowed us to change the way we think about fundamental physics. Nowadays, life isn't that easy. Instead, you have to look at collection of events, like the Higgs boson discovery was done by a whole bunch of noisy events together, because sometimes an individual event is noisy, maybe there are quantum mechanical effects, and you really can't make any conclusions from an individual sample. And also in astrophysics, we start to stack together information from multiple stars and so on to try to infer something that's common amongst all of them. And in particle physics, by now, of course, machine learning has revolutionized every piece of our data processing pipeline, as you've seen, whether it's simulation, reconstruction, or really separating the signal from the background right at the end. But the piece of the puzzle that has kind of remained the same all these decades is the final statistical inference step using the usual likelihood ratio tests and so on. And so if you had a new grad student that joined your group, you would probably hand them one of these books that were published before they were born. And by the time they've read it end to end, they are really up to speed with the state-of-the-art methods of doing statistical inference. The question is it time to modernize that? And probably the answer is yes. So just a reminder, our raw images are 100 million dimensional, and we do some very extreme data compression to bring this down to one number. This is the traditional way an analysis is done. You have thousands of samples, each of them becomes one number, you plug it into a histogram, and really this gigantic data set is compressed into just maybe 20 to 40 numbers. Right? And then you might have your prediction from your simulator that says that this is roughly what your data should look like. Your data, of course, looks like data. And then you might have different hypotheses, like the signal strength that changes the overall normalization of some signal. And you can compare the two and ask the question, given this data, what is the likelihood that mu is equal to 1 or 2 or 3, and so on. Right? And this is done by comparing likelihoods of the two different hypotheses. And of course, the Neyman-Pearson lemma says that if you had to compare just two, then the ratio of them would be the optimal test statistic. But in reality, we are comparing an infinite number of different hypotheses. It's a composite hypothesis test. And so instead, we take the negative log likelihood for that data, and we plot it for every possible hypothesis value of mu. It's often parabolic, doesn't always have to be. And then if you assume asymptotics, Wilks' theorem, you can draw a nice horizontal line here and say that everything below this line, the hypotheses are compatible with my data, and everything above I can reject at 2 sigma. And this is what we've done for a long, long, long time. Most papers from the LHC come out doing something like this. And so this is going to be my confidence interval, 2 sigma confidence interval. for some measurement that I've made. Now, we as a community often say that all of this doesn't need changing because it's almost optimal and every assumption we've made is well justified. So I want to talk about these well justified assumptions. One is that you can summarize your gigantic data into one variable. And that there's a kind of a self-fulfillment that goes on, because if that's not the case, what we do is we will split the data analysis problem into two different analysis problems. And if it's still too complicated, we'll split it again and again and again. And this is just one piece of a gigantic chart, at least from the Atlas experiment, how we split things. And by the time you split it enough, sure, that claim does become true, that maybe one variable is enough to explain that tiny part of the phase space. Even if it isn't, you have so little statistics that it doesn't matter what variable you use at this point. Another thing we say is we can rely on asymptotic approximations most of the time, but in reality, we also make data selection choices in a way to remove any problems that might arise in these assumptions. So you might make your analysis more coarse, but you're doing that by sacrificing fine-grained information that would be more useful, but would break your asymptotic assumptions. Then we have even more dirty things, like we claim that our nuisance parameters can be factorized, and the way you can make that true is by redefining your nuisance parameters in funny ways. And as a particle physicist, these are trade secrets that I'm not even allowed to tell other people how dirty these tricks can be. And the one that I want to insist on is related to this previous one. We say that we have thousands of samples, we're generating 40 million collisions per second, and so we live in this amazing world called asymptopia, and where the likelihood ratio is optimal and so on. And that is really something I would like to push back on, because it's a fundamental misunderstanding of our field, where we think we have lots of data, but all the new physics is always hiding in the tails of our distributions, almost always, because we all, particle physicists always want the next bigger collider, right? So the new physics is going to be just outside our reach. And so if we can improve our statistical analysis at these low sample size tails, then it would really improve our sensitivity. Okay, so let's try to address some of these challenges. Of course, for the high dimensional problem, we know that the answer should be simulation-based inference, neural simulation-based inference. The idea has been around for more than 10 years now, but it's only recently that it was ever applied to data. So what were the challenges? The first of all, of course, is robustness. Are you really going to trust a neural network to estimate some kind of likelihood ratio? What if it's wrong in some weird corner of the phase space? Or how to propagate systematic uncertainties or nuisances? How to do your inverting of the hypothesis test now in high dimensions? So these are the kind of problems that we worked on and solved through these couple of major publications from the Atlas experiment. And the solution was, instead of doing a traditional neural simulation-based inference, we use a semi-parametric approach where you're able to really get exact interpolation functions in a lot of places, and that makes the validation possible. And it really took away 6 years of my life, and I'm happy that I can move on to new projects. But essentially, this is the crux of what we did. We built this gigantic mixture model. So this is the likelihood ratio you want for any event X and some hypothesis values of mu and some nuisance parameters alpha. And you can write them down as functions. These are the functions that you know analytically. This is something you know from quantum field theory. This is something you will just make a well-guessed approximation. So you only need to estimate these two ratios using neural networks. So we do use neural networks to estimate density ratios. In fact, we use a whole bunch of them, each for some kind of physics process. So that's how this one is estimated. Then for your nuisance parameters, we estimate the impact of them using additional neural networks, so one per source of systematic uncertainty. And then you really have everything, except for the fact that the neural network estimates may not be exactly right. So in fact, each of these boxes is not one network, but 1,000 networks that allows you to somehow estimate the uncertainty of the training procedure itself. And that whole thing requires training 10,000 neural networks. It's a whole quite expensive, but then you can take advantage of the differentiability of this whole extended likelihood and go from there. And so after the 6 years of effort, this is the final result that we see. It's a negative log likelihood curve. You can compare this publication. So this dashed line is also a paper we worked on for, I think, 4 years and then published it using the traditional method. And then this is the NSBI version of the exact same analysis. And you can see this dramatic improvement in our ability to reject the null hypothesis. If this were to go up to 25, we could claim discovery of this new kind of Higgs process. So we made a big step in that right direction. Right, and this is really a flagship. Of course, LHC measures a whole bunch, hundreds of things every year, but this is one of the flagship measurements called the Higgs width. It is really something where the baseline was tuned as much as possible. So it's really a strong baseline to compare NSBI against, and we see this nice improvement that we get from high dimensions. And it's interesting to see that there was a tech news website that wrote a long form article about how we're using these new statistical methods to finally account for quantum interference in our collider physics properly. And there was also an article from the Atlas experiment talking about how the Higgs boson studies are now being revolutionized by AI techniques. I find it interesting that we started using buzzwords and the journalist was actually trying to explain the quantum mechanics and all of that very seriously. So talking about serious things, of course, the thing I should talk about is uncertainties of the neural networks themselves. How do we quantify that? We're training ensembles, and you can see that sometimes the ensembles disagree from one another. They're trained on bootstrap versions of the training data set, and sometimes they agree. So that somehow should give you an estimate of your uncertainty. Of course, there are many different ways to do that. But the one I really like is this paper that's come out called Wi-Fi ensembles, where they have a procedure to really calibrate these ensembles, give them weights. And then if you get your uncertainties from this Wi-Fi ensemble, with only 16 networks, you're able to recover genuine, reliable uncertainty. So you can get coverage. So this really shows you that if you expect, if you take a 2 sigma uncertainty here, you will really get 95% coverage. So I know that there are plenty of different uncertainty quantification methods out there, but I'm not aware of anything else that provides this kind of very solid frequentist coverage guarantees. And I was so impressed by this paper that I hired the student. She's going to be a postdoc with me soon. Another question that you might ask is, okay, you're using simulation-based inference. This whole thing relies on having a perfect simulator. What happens if you don't? And in fact, the answer is that you don't necessarily need a simulator for SBI. So Oz, who just gave the previous talk, has also worked on SBI and shown that you can learn from the data itself, other parts of the data, which are control regions, and then interpolate into the signal region if you don't want to trust a simulator to model what's going to happen in the signal region for you. So you can combine SBI with data-driven backgrounds. So it's a cool paper. Okay, but this is all talking about ways we can improve the traditional likelihood ratio test by introducing high-dimensional methods in every piece of the pipeline. But what if I wanted to question the test itself? Again, this is something I would not dare to do at a particle physics conference. It's a heresy to question the likelihood ratio test. But hopefully the group here is kinder to me. And remember, the Neyman-Pearson lemma only says that it's optimal to compare 2 hypotheses. And we're not doing that. We're comparing an infinite number of hypotheses. And so there is no guarantee. There's no proof that the likelihood ratio test is the best thing you can do. And for a long time, me and my colleagues thought, yeah, but it's just a question of someone sitting down and writing the proof. But of course, here at CMU, several of you knew that that's not the case. Annelie's group has been working for a long time on designing statistical tests with optimality guarantees. So we worked together on this paper where we compare the likelihood ratio test with something called the focused test statistic, where the denominator is switched from just the maximum likelihood estimate to an integration over all hypotheses that are relevant in the test, weighted by some function f, which we call the focus function. This function allows you to assign which hypotheses you care about more, which are the physics-motivated hypotheses. So it kind of lets you assign where you want to trade off the power of the test. You want more power here, and then there's no free lunch, so you lose power somewhere else. And this is tested on a Higgs data set. So this is the traditional likelihood ratio test. And you can see that we're not even in some very low sample size regime. You get straight lines for the critical values, which means that we are in supposedly the asymptotic regime. And this is FTS, and you can see that after calibrating correctly, the FTS is already smaller. The calibrated confidence intervals, expected confidence intervals are on average smaller than for the likelihood ratio test. Right, so the day I saw this, it was really really shocking, really impressive. And so the focus, this becomes particularly useful as you go to low sample size regimes. And as you can see, you can't rely on Wilks anymore, so you really need to do some kind of critical value estimation very quickly, and that's something you can do with machine learning. But just to get an idea for why this seems to work better, if you have a likelihood ratio test, so we're going to see a very simple example where you just do one measurement, and that itself, so you get a test statistic that is between -6 and 6. And so you're calibrating it this way. You're saying, if the true value of your parameter is 0, then I will accept, within this region of the test statistic, I will accept it. Everywhere else, I will reject that hypothesis, and so on. You can do that for every value of mu, and then you invert it, right? So when you get some data, let's say you measured data at 0, then you say that, okay, so the data, all of these hypotheses are compatible with the data, and everywhere else it isn't, right? And for LRT, these bands are all the same width, no matter which hypothesis value of the hypothesis you're testing. For FTS, you do a trade-off. So you focus your power here. So these bands are narrower here, and you sacrifice the width over here. So it becomes narrower here and wider here. So if the data happens to be here, when you invert it, you get that the final confidence interval is a lot smaller than for likelihood ratio. But if you were unlucky and the data was here, then it would be larger than the likelihood ratio test. So you're making a bet, you're making based on your guess on what is a more reasonable part of the parameter space, you can make this choice. In fact, you can optimize this on your simulations. You can try a whole bunch of different focus functions, wider focus function, narrower focus functions, Gaussian, something else, and see which one gives you the best overall sensitivity, what is the worst case scenario, best case scenario, and so on. So as long as you don't look at data and you optimize just on a blinded analysis, you can really optimize the focus function and then go from there. The challenge is, of course, now FTS can't rely on Wilks, so you really need to estimate your critical values in some other way. For example, 68 and 95% confidence intervals. So the way we do this traditionally is you have generate a whole bunch of pseudo experiments for some true value of the parameter, let's say mu equals 0, and then you would find the distribution of the test statistics. Say, okay, if I cut here, then everything below and accept everything below this, then 95% of the time my true value will lie within my interval. But that's only for 0. Then I need to do the whole exercise again for 1. Mu equals 2, mu equals 3, and so on. And each dot that you see over here is this entire exercise, expensive exercise that's been done. And then you can compare that to your test statistic and say, okay, this, where it intersects, is my calibrated confidence interval when you can't rely on Wilks, right? And if you think about it, this assigning of these lines here is a question of determining quantiles. So why not use quantile regression? Of course, this is the ideas folks at CMU have been thinking about for a while. And so here you can see how that would work for the likelihood ratio test. So these are the critical values, and you can see that with quantile regression, by using a couple of orders of magnitude less simulation budget, you're still able to get the level of accuracy that you would by doing with much higher budget of for simulation if you did the traditional way. So now suddenly you can actually estimate your critical values very quickly, and you can use more powerful tests like the focus test statistic. And if you can do it for likelihood ratio, of course, you can do it for FTS as well. So now that all these challenges are out of the way, you can finally apply it to a benchmark Higgs-ML data set. This has been around, I think, since 2012 or 2014. So it's really a data set that people have used across the field. It's you can't cheat on this data set. And so we're going to see if the FTS does better, and if so, in what regime. So we're going to compare two versions of FTS, one with a wider focus, one with a narrower focus, always at the standard model, which is our best guess of what the true value of the parameter is, which is at 1, right? And we see, so here, the narrower your median confidence intervals, the more precise your measurement is. And remember, the confidence intervals are always valid because we construct them to have coverage no matter what. And so we see that on average, the confidence intervals are narrower for FTS across this parameter space between 0 and 4 if we use this wider focus, even if you're wrong. So if you put the focus at 1 and the true value is somewhere here, you're still doing better with FTS. So there's quite a lot of robustness to focus misspecification. If now you use a narrower focus, then the gains here are bigger, sure. But then you are taking a risk, because if the true parameter is here, then you actually would have done better by using the likelihood ratio test. Right, so there's a trade-off, and I'm actually curious, which one would you choose? If you were doing a Higgs measurement, at least amongst the particle physicists here, would you choose the wider focus that gives you a little bit of gain, or the narrower focus that gives you a bigger gain? Narrower? Who said that?
What year is it? 2014?
Yeah, this data, you're right. This data set is from it's a 2012 Atlas data set. So yeah, that's a good point. So maybe you want to be a little bit wider to cover yourself. Yeah, good. So indeed, there's a choice to be made, but it's a choice you can make before you unblind. You should absolutely not change it after unblinding. Cool. And so there's a nice little article that came out on Nature about a student overturns long-held belief in particle physics, and that student is sitting in this room, James. All right, and it kind of makes us look like fools, but it's always good, I think, when a physicist get their egos challenged. All right, so we have another study. This is a dark matter search where by default you would think the particle doesn't exist. So instead of the focus being at 1, it's going to be at 0. 0 indicates that the thing doesn't exist. And this is what the signal would look like. This is what the background would look like in 2D. And again, we can do this comparison of, we put the focus at 0, and then we say, we change what the true value is, right? So all of this is misspecified focus. And we see, even with the misspecified focus, FTS is super robust and gives you smaller confidence intervals compared to likelihood ratio. For both the wide focus and the narrow focus, of course, at some point when you have the narrow focus, the FTS will start getting worse than likelihood ratio at mu equals 15, which is really, really high. Like if we had 15, we would have discovered this particle already. Yeah, so the point is, even if you put the focus here, you still get sensitivity in other places, and the coverage is correct, so you're good. But there's a discussion sometimes that comes up about bias, and indeed, FTS is biased in the technical sense, but not in any sense that I would say is useful or meaningful in our measurement. So what we care about is the confidence interval should cover. Right? So 95% of the time, the true value should lie within that confidence interval. That is guaranteed by this method. So bias here means that you accept, your confidence interval may accept some other value of mu more frequently than it accepts whatever the unknown true value of mu is. So if let's say if your focus has been placed slightly in the wrong place, FTS will more frequently accept this value of mu than the true value over here. Right, but that, I would argue, doesn't matter. That point also moves depending on the true value and the data and so on. And in the end, once you look at the confidence interval, it still gives you the correct coverage. So yeah. Also, using a bias test is nothing new in particle physics. We've been using something called the CLS method for years and years and years, which we know is biased. We do it. The motivations are slightly different, but we deliberately bias our test to solve some problems. And of course, the statisticians here will know that, especially when you do high-dimensional analysis, even for point estimation, you prefer a low variance estimator over an unbiased estimator. So hopefully this is all in the same spirit. Okay. But if at least the particle physicists are worrying that, oh, it's biased, but maybe that means that I will not be able to reject, if I put the focus in the wrong place, maybe I won't be able to reject that point easily. So we can test out that idea. So you remember for the dark matter search, the focus is placed at 0, right, centered at 0. And we're going to check how that affects, if the true signal actually exists, will we be able to reject this mu equals 0? And that means setting lower bounds. And we can see that, in fact, FTS allows us to set better lower bounds, so higher lower bounds than likelihood ratio. So that's good. And similarly, for upper bounds, if there is no signal, then FTS is able to set lower upper bounds, which is also the desired effect. So I'm showing it to you for 2 examples, but here you can see for a range of true values, we're able to set both better lower bounds and upper bounds with FTS compared to likelihood ratio across the board. All right. So with that, I come to my conclusion. Hope I've talked about how semi-parametric NSBI is really being used now in particle physics and is transforming the way we can extract information from high-dimensional data. And with FTS, now we can also beat the likelihood ratio test itself. And a combination of the two would really give us control over these high-dimensional spaces that we've traditionally not been able to handle. And I mean not just in the high-dimensional data space, but in the high-dimensional parameter space. And finally, if nothing else, you remember nothing else from this talk, hopefully you remember that this concept of asymptopia is a misconception, in my opinion, about our field. We are always studying the tails of our distributions, and we are always in like low signal fraction, low sample size regimes. And this will always be the case, no matter how many colliders we build. Thank you.